Panel C shows the geometry during the lunar eclipse. So the width of the Earth's umbra at the moon is 9,200 kilometers. This here is 7,000 kilometers. Okay, so it's much more common to observe the total lunar eclipse. Also, the moon could be actually, depending on precise orientation of its orbit relative to the Earth's orbit, could actually be located in the partial shadow, in which case one observes the partial lunar eclipse. Panel D again illustrates, again, the panel C is just drawn not to scale because of the sake of, for the sake of clarity. In panel D, you have things drawn to scale. Okay, so here in the top panel, again, is geometry for the total solar eclipse, and this is the actual photograph of the total solar eclipse. So indeed, you can see the sun's, the lower atmosphere is only a few thousand kilometers, right? The upper atmosphere is much more extensive. It's tenuous, but it's very hot, and you can see it glowing here, right? Because of its high temperature. Okay, here we have geometry for the total lunar eclipse when the moon is in Earth's complete shadow. And this is how it looks. You can ask the question, well, how come I can see the moon when it's in the Earth's complete shadow, right? This here photograph shows that, you can see it. So how is it possible? The clue to the answer is the fact that during the total lunar eclipse, the moon always appears to be reddish. And here's what's going on. The fact is that if the Earth didn't have any atmosphere, we wouldn't be able to see the moon. So here is the Earth, and here is the Earth's, say, the top of the Earth's atmosphere. This is again not drawn to the scale because the top of the Earth's atmosphere is about 20 kilometers above us, right? But just to make the point, and say here is the moon. It turns out that when light goes from one medium to another, the sunlight consists of actually all different colors, the entire spectrum. And different colors mean different wavelengths of light. And it turns out that different wavelengths are bent by a dense medium like our atmosphere by different amounts. And it turns out that the red light is bent more by the Earth's atmosphere than the blue light. So here comes the sunlight. So the longer wavelength red light is bent more by the Earth's atmosphere than the blue light, which just zips through. Anyways, wavelengths longer than red. Okay? So the same thing happens here. The Earth's atmosphere bends the red light more than the shorter wavelength. So that red light is directed to the moon. It's focused, if you will, by the Earth's atmosphere. It acts like a prism. And then what we see is this red light reflected off the surface of the moon. So if the Earth didn't have any atmosphere, of course, none of the wavelengths would be deflected. And indeed, we could not see the moon because it would be in Earth's shadow.